Hello guys, Moritz here, and today I'm going to show you how I built my own uninterruptible power supply for the Raspberry Pi in this case. And today I'm going to talk about the circuit and how I designed it, and let's get right into it.
This video has been brought to you by JLC PCB, the largest PCB prototype enterprise in China and high-quality manufacturer specialized on PCB prototypes. Upload your Gerber files for quality review and order high-quality PCBs for affordable prices to turn your project into a real product. Order now and get free shipping on your first order.
So here you can see an overview of the whole circuit. I've cleaned it up a little bit and put it into small blocks, so it's much nicer to get an overview of everything, because if you're new to this circuit can be a little complex for you, but don't worry, I've got you covered. So I've used KiCad for designing my circuit, which is a program where you can build your own schematic by adding parts and stuff like that, and then use its PCB editor to build your own PCB and make all the traces and such. So before we get into the circuit right here, I'll tell you one thing that is always a good thing to check out, which is electrical engineering, and that's where I've got some advice on my UPS design. Not only about the charging circuit right here, but they have got a lot of resources and information about what to do and what not to do, so I will put in the link down in the description. So let's get back to the circuit. Up in the left corner we've got our input side, where we've got a 12-volt barrel jack and a connector where you can connect something like a fan. Down here we've got our micro USB and a little capacitor across ground and 5 volts just to smooth it. And then we've got these labels. So in KiCad we've got these global labels which connect traces to other traces. For example, this 12 volt is connected to this one right here, and the direction tells you that this is an output of this part and an input for this part, always indicated by this arrow. Let's start with the buck converter. The buck converter takes the 12 volts and puts out 5 volts regulated, and it does that by using this diode and coil. And you set the output voltage by changing the values of these resistors and capacitors, and all you need to do for that is use a formula that is described in the data sheet. So let's look at the data sheet real quick, this one. So as you can see, I found this part by searching for step-down converter and 3 amps, because I wanted the circuit to be able to supply 3 amps continuously. And in the data sheet of the part you will always find a typical application. So this is a typical application if you want to get 3.3 volts out. A nice side effect of this part is that it has a wide input range from 4.5 volts to up to 28 volts. So you could even plug in a solar panel or something into the UPS and use that as a power source. But as you can see, the typical application for 3.3 volts has these component values. So if you want, for example, a circuit where you need to regulate to 3.3 volts, you could use this arrangement. To get other voltages, you will have to read the whole data sheet and also look at these parameters, because, for example, the feedback voltage, which is typically around 0.8 volts, will get in handy down in the formulas to calculate the component values. So if you go down here, application information, component selection, you can see a lot of formulas, and you will have to put in, for example, here the feedback voltage, your desired output voltage, and then you can calculate R2 and R1 from that. You will have to change the formula a little bit, but I think that's pretty easy because it's simple math, and you will do that for everything. Also, you can calculate the inductor that is needed, or the coil. As you can see in KiCad, that we've decided to use a 4.7 microhenry one, and that has a reason, because if you look here, it says a larger value inductor will result in less ripple current that will result in lower output ripple voltage. However, the larger value inductor will have a larger physical size, higher series resistance and or lower saturation current. And because of these 2 points down here, or because of size, we decided to use a smaller one, and because it has a lower saturation current. You can also calculate the peak-to-peak ripple with this formula here. It helps you to choose the right parts. So let's get back to the circuit and let's follow the 5 volt buck going out, and this goes to the voltage source selector. This is essentially the heart of the whole circuit, because here the correct input source gets selected, and we have got two LEDs that shows the state of the whole UPS circuit for the user. And the cool part about this is that there is no microcontroller needed for the circuit, so this is just a simple circuit that works on its own. If we analyze it, we've got one MOSFET up here, one down here. So these are P-channel MOSFETs, and they are P-channel MOSFETs because of a specific reason. You've got the 5 volts coming in from up here, and this MOSFET gets pulled down to ground with this resistor. So whenever there's no voltage coming from our buck converter, this MOSFET will turn on and let current flow from 5 volt USB down to V selected. And whenever our 5 volt buck converter kicks in, it will pull up the gate of the MOSFET and thus turn off the MOSFET itself. So 5 volt USB will be disconnected, and only the 5 volts coming from the buck converter can flow through the circuit. And that's why also this diode is here to join 5 volt USB and 5 volt buck. And this diode is also here to protect against current flowing the other way, because you don't want current to flow back into the buck converter, because that can ruin your day. Another thing that you should know is that this MOSFET right here is specifically placed in that direction, with drain connected to 5 volt USB and source connected to the rest of the circuit. Because if we look at the data sheet, you can see that it has a body diode, which is the one over here, which is connected from drain to source. So whenever you use a MOSFET, keep in mind that it has this body diode, because as I told you, if we would turn around the part, which would also work, still current could flow back into the 5 volt USB, and that could be bad. So always keep that in mind, that the diode should go into the right direction, so current can only flow in one direction. And this is also why this MOSFET down here is connected this way, so no current can flow back into the battery, because obviously the battery will not like that. And this MOSFET down here also has a pull down resistor, which is over here, so it's not really clear that this is the pull down resistor for this MOSFET, but as I told you, it's right here. So this MOSFET right here kicks in whenever there is no voltage coming from the buck converter or the USB, and that will let current flow from the battery down to V selected. We've also got a diode up here, so no current can flow back into the circuit, so that way the battery cannot charge itself. Over here we've got two LEDs that show the state, and this is really nice design, because the green LED is connected to 5 volt buck and 5 volt USB. So whenever this potential is higher than the potential of the battery, the green LED will light. So whenever there's no voltage coming in from the buck or boost converter, this potential will get lower, and now the red LED can turn on. So these are all discrete components, and that is why this circuit works so well, because there's no other electronical parts included other than these discrete components, so it's really fast. And let's follow the V charge and the battery connection, because those go to the battery protection and charging circuit. And this is a pretty common circuit that you will find a lot, so let me show you. What this essentially is this circuit right here, and I think every one of you will know that. So this is a pretty little board that you can use, which has charging indicators because of the TP4056 charging controller. You can plug in 5 volts over here. I think they've got the labeling wrong, because down here this would be the protection circuit and this the dual power MOSFET. And essentially what I did, I just used exactly the same circuit as here, with one little modification. In my circuit I've also connected a small potentiometer to the programming input of the TP456, because that way you can select the charging current from, I think, 1.5 amps down to 0 amps. So you have a wide choice for your current. But the rest of the circuit is pretty much the same. It'll take the battery plus, and the battery minus is obviously not connected directly to the battery, but rather through the protection circuit. And battery minus is then connected to ground. Yeah, so I think there's something wrong here in this circuit. So there should be a connection to ground for battery minus, because I think yeah, it's connected to the ground of the charging circuit. And so there should also be a little ground connection down here, so let's add that. And now the circuit should be correct again, I think, yes. Then we see, if we go back to the voltage source selector, we've got a little MC VCC down here and V selected. So let's follow the MC VCC, which just goes down to a little 80 tiny. And this one controls the output and the Raspberry Pi. So it has some inputs and outputs right here. There's an optional programming header, which is not included on the PCB because it's optional. So essentially to the microcontroller there's a button and an LED connected, or terminals to connect a button and an LED, so the user can connect his stuff right here and control the whole board. And on the other hand, the microcontroller is connected to our Raspberry Pi, and Pi on is a signal coming from the Raspberry Pi when the Raspberry Pi is successfully powered up, and Pi control is the control line coming from the microcontroller going to the Raspberry Pi, where the microcontroller can tell the Raspberry Pi to shut down. And Vout is obviously the output of the whole UPS circuit. So if we now follow V selected, which can either be 5V USB, 5V buck, or the battery. Oh, I forgot something. So also what you need to keep in mind while designing such a circuit is, if you have diodes in your circuit, these will have a voltage drop. So keep in mind, let's go back to one of the data sheets. So here I've got the data sheet for our diode. So what you need to check out here is down here the maximum instantaneous forward voltage, or VF, and this will tell you how much the voltage will drop. So at the diode 0.5 volts will drop. So if you got an input voltage of 5 volts, the voltage after the diode will be 4.5 volts. So you will have to keep that in mind while designing your circuit. So whenever you have this buck converter, you will want to set the output voltage a little bit higher, for example 6 volts or something like that, because it will drop if it goes across this diode. So we've got two diodes coming from the 5V buck converter, so you can think that there will be 1 volt of voltage drop. So you will have to set this one a little bit higher than the output voltage. Another thing I should mention is about these MOSFETs, because these, if you substitute any of these parts, you will need to make sure that they have almost the same values, and there is one specific one that is really important. If we again look at this P-channel MOSFET, we have this RDS on. And as you can see, this is the resistance between drain and source when this is turned on. And you can see it's pretty low, because obviously this is the state in which the MOSFET is turned on and current can pass through it. And as you can see, it has also this VGS voltage, which is the gate source voltage down here. And if you draw around 4 amps, this voltage has to be at least 4.5 volts, so the resistance gets really low. So you will want to have a pretty low VGS voltage. In this case, for P-channel MOSFET, this is always a negative number. If you look at an N-channel MOSFET, this is always a positive number. So you want to get this voltage as low as possible, because otherwise it could happen that the MOSFET will not turn on when a voltage is applied, or it will not turn off if a voltage is applied. It depends on whether you're using a P-channel or N-channel MOSFET. So you will want to have this voltage really low for N-channel and P-channel MOSFETs, because otherwise the circuit will not work. So going back to the circuit, we can now look what's at the end of V selected, and there we've got a boost converter, and the boost converter takes the input voltage and boosts that up to 5 volts. So you might be wondering, why am I inputting 5 volts from the buck converter or 5 volts from the USB into a boost converter, because they should already be 5 volts. Well, there are actually several reasons why I'm doing that, and one of it is because of the voltage drop of these diodes. So if we put it back into a boost converter, we will have a pretty stable output voltage, even if things get switched around on the input side. Another reason is because if we switch from the buck converter or USB input to the battery, this boost converter will already be running, so when switching from the powered to the unpowered state where the battery has to power the Raspberry Pi, it will be much faster for the boost converter to accommodate for the voltage change on the input than if we would have changed the circuit and only connected the battery to the boost converter. It will take much more time for the boost converter to kick in, and thus we will not have a really stable output. So for the selection of the parts for the boost converter, the same applies as for the buck converter. And if we go and have a look at the data sheet, you can see we've got a 2 amp step-up converter, but it is capable of 4 amp switch current, so that's fine. We can get 3 amps out of there. And you've again got a typical application down here where all the parts are labeled, and you will also read the whole data sheet. And somewhere down at the bottom you can see how you can set the output voltage with R1 and R2, and it has something on diode selection, all the parts you will need for this circuit to work. So the data sheet is always your friend. If we follow the 5 volts boosted, it will go to the output protection and control, and the 5 volt boosted also goes into another MOSFET right here, which this time is a N-channel MOSFET, and this also has a specific reason, because as you can see there's this control pin right here, and it's also got a pull-down resistor to ground, which will turn it off in the neutral state. And if we follow the control, it goes to our microcontroller. And the reason why this is a P-channel MOSFET is because the control also goes to the MT3608 boost converter. So we can use the same pin on the microcontroller to turn off the boost converter and turn off the output power. So we won't have to use the boost converter whenever we are not using the output. So we can control the output right here with the control pin as well as the boost converter, and that's why this is a P-channel MOSFET. The output of that passes through a little resettable fuse, which will auto reset if it has blown. And then on the output we've got our Vout, which goes to the Raspberry Pi, and a little USB port where you can plug in something else like a hard drive or something. And then we've got 4 capacitors for output voltage stability. Another thing on the voltage source selector, the voltage of the battery is also going to our microcontroller, and that's because we can read the input voltage on the microcontroller that it is supplied with, and thus we can tell whether the battery is charged or not. So whenever the battery gets down to 3.5 volts or less, the microcontroller can sense that and tell the Raspberry Pi to turn off. So that's the whole circuit covered, and let's try it out on our test bench. So let's try to test the circuit. Unfortunately my Raspberry Pi is currently not working, and I have to figure out why. So we have to test the circuit with something else, and I've got this little LED tree here that I've built myself, which is connected to the USB port on the uninterrupted power supply. And this port is essentially the same as the one that's connected through the header to the Pi. So there's no difference in plugging something in here or to the Pi directly. Down here we've got our button input and our LED, which you probably can see, which is down here. And over here I've connected a Raspberry Pi. So the orange LED, which is this one right here, will tell us whether the Pi is turned on or off. So this is the signal that's coming from the Pi to the uninterrupted power supply. So this, when the Raspberry Pi is booted, should be high, so the LED should light. And the red LED down here is the control coming from the board to the Raspberry Pi. So whenever this gets high or the LED lights up, the Raspberry Pi should shut down. And we are going to simulate that. I will connect this LED and the pin which is going to the board to VCC, or 5 volts potential. And with that I will simulate that the Pi is booted up and send his signal back to the board. And then when I press the button or the switch down here, we can then turn off the Raspberry Pi, and then we will see that the red LED will turn on, which will tell the Raspberry Pi to shut down. We will simulate that by turning off this signal that's coming back from the Pi, which will tell the board that the Raspberry Pi is shut down and we can turn off the power. So let's try that. First of all, we will have to turn on the PCB, and I'm just going to do it like so. So now if we press the button, we can turn on the Raspberry Pi and you can see the tree is lit up. Also we get a green indicator down here and a red indicator up here, which tells us that first of all the Raspberry Pi is turned on, or the power output of the board is turned on. And this one up here tells us that we are in battery mode. If I now get a power bank, which we can use to simulate a power input, I will plug that in right here, and you will see that the status of the LEDs up here changed. Now we got a green LED and a blue LED. The blue LED indicates that the battery is now being charged, and the green LED indicates that we are running on external power, not on the battery. So when I unplug this should simulate the case where we have a power outage, and you can see the tree is still lit up, so no problems there. And now I will simulate that the Raspberry Pi is turned on by pulling this LED high. Now the board knows that the Raspberry Pi is booted up successfully, and now we can try to turn it off. For that we will have to press the button for a few seconds and it gets indicated by the light. Now you can see that the board is waiting for the Raspberry Pi to shut down and send the signal down here, so you can see the red LED is lit up. And if you now simulate that the Pi has shut off, I will remove this wire. You can see it stays on for a few seconds and then turns everything off. So now everything is shut off. Now we can turn it back on again. So in the case where your Raspberry Pi doesn't boot, or you just want to shut it off completely, like a reset or something, we can hold the button for a few seconds and we get the indicator that we can now shut it off. Or we wait a little longer, and when the LED turns off it will shut down the whole board and you can release the button and everything is turned off. So another nice feature is that you can either use a button or a switch, a sliding switch, which is down here. And all you have to do for that is just unplug the power or the battery so the board is powerless, plug it back in and then turn on the board with the switch. So now the board has turned on. And we can now again simulate that the Pi has booted. So we will put this wire over here. So the LED is turned on, just for you to see. And now if we slide the switch over to turn everything off, you can see now we are in the state where the green LED is blinking, the red LED is on, which tells the Raspberry Pi to shut down. And if we now undo this wire right here, the board will know the Raspberry Pi is now shut off. Wait a few seconds and then cut the power. So that's it. As you probably already read in the video title, I will be giving away one of these PCBs to one of my viewers. And to enter the giveaway, all you need to do is subscribe to my channel, give this video a thumbs up and write a comment about why you would like to get one of these PCBs. And then I will pick a lucky winner in 2 weeks from now and send you the PCB. But still keep in mind that those are prototypes and that there's no warranty whatsoever. So I hope you like this video and I will see you next time. Bye!